Example 3. Construct a polynomial function with the following graph. So we're given this graph of a polynomial function. We can see it's smooth and continuous, no sharp corners or cusps, no holes or gaps. It's definitely a characteristic polynomial function. But all we can really see is that this general snake shape, and we can see 3 x-intercepts. But it turns out those are the most important things we need in order to make a function. So we can see from the graph our real zeros, our x-intercepts, saying the same thing, are -3, 1, and 4. So you can see them here. -3, 0, 1, 0, and 4, 0. So we know then if -3, 1, and 4 are the zeros, we can make factors. So if we have our function f of x, we'll have a generic constant in the front, and we'll talk about that in a second. So we know that if -3 is a zero of our function, x minus -3 will be a factor of our function. If 1 is a zero of the function, x minus 1 must be a factor. And if 4 is a zero of the function, x minus 4 must be a factor. So we've got our minus minus here, which just becomes plus. So now we have to talk about the coefficient in the front. Let's first assume the easiest case, an a value of 1. So if we choose a equal to 1, that will give us f of x equals x plus 3 times x minus 1 times x minus 4. So let's look in the calculator. So I enter the function here. Now the window, I'm going -5 to 5 on the x-axis with a scale of 1, and on the y-axis I'm going -30 to 45 with a scale of 5. Again, not the only correct window, but it's going to be good for the examples I'm going to show you here. So if we graph, that certainly looks like the shape given in this problem, the blue snake shape. Now, as far as the steepness, the y values, we don't have any information about y values here on this given problem. All we know is those zeros. So an a value of 1, as we have here, this is one option. Now, let's change that a value to a 2. So I'm going to insert a 2 as the a in the front. So if I graph, I can see it still has those same x-intercepts, -3, 1, and 4, but it looks steeper or more vertical, which makes sense if you think back to transformations. If you multiply a 2 out in the front of a function, it makes it twice as steep. And then, if I change that a value, I'll make it a smaller than 1. I'll go down to a half, 0.5. As you can imagine, compared to the a value of 1, it's only half as steep. Almost looks like the idea of a vertical compression, but it still has those same x-intercepts, -3, 1, and 4, which is all we can really be sure of on our given function, the blue one in the example. But now, if I insert a negative sign, so now my a value is a -0.5, we can see the graph has reflected about the x-axis, again, which makes sense with what we know from transformations. If you multiply a negative in front of the function, it reflects it about the x-axis. But it still does have the same x-intercepts, -3, 1, and 4, but since the shape's changed here, we know that that could not be an option for our blue graph here in this example. But that a value then can be any positive real number. So a can be any positive real number. It just can't be negative because that would reflect that shape. So the easiest way to answer this problem would be you choosing an a value of 1, but you could choose any value out in the front, a 2, a 1/2, as long as it's positive. Oh, and if you guys want to note your viewing window in here, so when you're looking back in your notes, we went -5 to 5 on the x-axis with a scale of 1, and then on the y-axis we went -30 to 45 with a scale of 5.